Hello. Ah. Good morning, participants. I welcome everyone for the fourth day of six-day faculty development program on emerging trends in sustainable manufacturing, advanced materials, and additive technologies. On behalf of Vailtech Multitech, Dr. Rangarajan, Dr. Sagundala Engineering College. Today's our guest speaker is Dr. Sugnesh AP. Before starting the session, I would like to introduce Dr. Sugnesh AP. Dr. Sugnesh AP is an assistant professor in Department of Mechanical Engineering at Arpagam College of Engineering, Coimbatore, Tamil Nadu. He earned his bachelor degree in mechanical engineering, completed his master degree in engineering design with distinction, and obtained his PhD in mechanical engineering from National Institute of Technology, Puducherry. His doctoral research focus on contact stress analysis of thermoplastic gears using finite element analysis and photoelasticity, contributing significantly to understanding of polymer gear performance and failure mechanism. His primary research interest includes computational mechanics, FEA, machine design, biomechanics, bio-based engineering materials, tribology, polymer composite material, engineering optimization, and additive manufacturing. His work combines advanced computational technique with experimental validation to solve complex engineering problems in both mechanical and biomedical application. Dr. Sugnesh has authored several research papers in reputed peer-reviewed international journals and conferences. His recent research focus on biomechanical evaluation of dental implant system, particularly the analysis of all on four mandibular implant configurations using integrated experimental and FEA approach. He has extensive experience in computational modeling using ANSYS Workbench, CAD-based product development, stress analysis, and the structure optimization. As an academician, Dr. Sugnesh teach undergraduate, postgraduate course in machine design, strength of materials, FEA, tribology, computer-aided design, and engineering graphics. He actively supervises students' project and encourage integration of computational tool in engineering education and research. His teaching philosophy emphasizes problem solving, innovation, and industry-oriented learning. Beyond teaching and research, Dr. Sugnesh actively contributed to curriculum development, FDPs, technical workshops, international conference, etc. He served as a reviewer for the reputed international journals and committed to prompting high-quality research in mechanical engineering and computational biomechanics. His current research aims to develop sustainable engineering solution through integration of bio-based material, computational design, artificial intelligence, and advanced simulation technique. Dr. Sugnesh believes that the future of engineering lies in the interdisciplinary collaboration where computational engineering and sustainable material and biomedical innovations covers to address global technological and social challenges. His ongoing efforts contribute to bridge a gap between academia, research, and industrial application, fostering innovation in next generation mechanical and biomedical systems. On behalf of Vailtech Multitech, Dr. Rangarajan, Dr. Sagundala Engineering College, I would like to welcome Dr. Sugnesh AP, and he will deliver the topic on bio-based and eco-friendly engineering materials. Thank you, sir. The session is yours, sir. You can continue. Thank you, sir.
So, warm and pleasant morning to one all. Am I audible?
Yes, sir, you are audible, sir. I will stop my presentation, sir. You can start your PPT, sir.
Yeah, sure. Whether my screen is visible, sir? Arvind, sir?
Sir, yes, sir. Sir, your voice not audible, sir.
Am I audible?
Now it is okay, sir. You can share your screen, sir.
Yeah. Am I audible, sir?
Yes, sir. You are audible. Yes, sir. Your screens are visible, sir.
Okay, fine. So, very warm, pleasant morning to one and all who joined for the 6 days faculty development program on emerging trends in sustainable manufacturing, advanced materials and additive technologies, ESMWT 26, conducted by Multitech Dr. Rangarajan, Dr. Saguntala Engineering College. I myself thanks for the opportunity by the Well-Tech Multitech Engineering College to deliver the such a wonderful topic on bio-based and eco-friendly engineering materials. Based on this bio-based and eco-friendly engineering materials, what will be the opportunities, challenges, and computational design approaches with its application in biomechanics as well as in some other engineering applications like polymer gears. So, I myself, Dr. P. Sugnesh, completed ME PhD and I am working as an assistant professor in the Department of Mechanical Engineering at Katpagam Engineering College, Coimbatore. So, coming into the agenda, so what we are going to learn within this, what we can able to as a faculty, as a research scholar, as a student, all of them are attending the FDP, if I am right. So everyone will come across with the materials, different different processes, how to process to get those materials. So how to classify these materials, so how to analyze those materials. So likewise, so n number of things based on your engineering terms, we can able to study in terms of a concept. And as if the faculty and research scholars, we can able to have a chance of that using that material into some particular applications and to develop some new materials or to adapt some new technologies to elaborately or extensively or to enhance the performance of the systems. So likewise, we will be having a more exposure on this materials and process and methodologies and adaptation of processes likewise. So from based on you will be having some collective things in your mind. So now I am going to give some glimpse and at last of the presentation I will come across with the real-time applications, what we have carried out and what technology we have adapted, how the analysis has been made. So likewise we will see. Before that we will be touching up with some basics which we have required or essential for the engineering knowledge to gain or to get some inference about the bio-based or eco-friendly materials. Okay. So in this agenda, we are going to see about the bio-based materials. What are all the materials, classifications, source, properties, and processing of the bio-based materials. Then computational design approaches. So like finite element analysis, multi-scale modeling, machine learning, digital twins. So likewise, those tech approaches, different approaches we will be going to see. Then follow with some applications in the biomechanics. So dental implants, orthopedics, prosthetics. So likewise, some applications we are going to see in this. How the biomaterials which will be applicable in the biomechanics. Okay. So then, what will be the challenges and future directions, key takeaways, we are going to see on the as a fourth thing. Okay. So first, so what you can able to infer. So if you end of the session, how you can able to classify what is the inference you can able to get is what will be the bio-based, biodegradable, bioresorbable, and eco-friendly materials with the precision. Then describe some mechanical structural behavior of the materials used in engineering and the medicine field. Then how finite element analysis and modeling, multi-scale modeling, then machine learning will be used to, as by utilizing the which will be approaches will be used for the biomaterials for manufacturing or synthesis or to analyze the behavior of the biomaterials. Then some case studies followed by with some limitations. So these are all the things you can able to infer from this upcoming slides, and we are going to get some inference. We'll be getting knowledge about the biomaterials which will be used in the biomechanics. So as an introduction, before getting into the topic, so as we have some statistics, so why we want to go with that? So why this topic is chosen? Why biomaterials? Not some, polymer material or composite materials or metal matrix composites. A number of material combinations are there. Why it is been focused mainly on biomaterials and eco-friendly materials and sustainable materials. So likewise, we'll be having some database which will be having a 400 metric tons of global plastic production per year in have a statistics. So on this, a small fraction is effectively recycled. So apart from that, everything will be as it is sent back to the earth. So based on that, 70 to 85% of your solvent used reductions or some composite bioprocessing which will be are not carried out, are not concentrated. So only 20 to 30% will be concentrated based on your production and cost reduction. So out of this 100%, only 20 to 30% only will be having some techniques to recycle or to reuse that utilized products. So main focus is turned into a biomaterials and eco-friendly materials, which will be switching over by replacing this polymer or metal based kind of materials, so that we can able to make a huge impact on the energy saving and process everything. In all aspect point of view, can able to save such a small amount of saving of energy is a huge impact on future. So that will be the main concept why we are choosing and targeting and focusing about to the biomaterials and eco-friendly and sustainable materials. Okay, so some of the engineering terms. So in engineering, how we can able to connect nature with the engineering. Okay, so first of all, it doesn't take an example to anywhere else. We just see as ourselves as an example. So ourselves will consist of body will consist of by using your bone, which will be having some hierarchies. So that will be have some self-healing properties. So bone itself has some n number of properties will be having behaviors. So such behavior till or not up to the mark, they have analyzed and they have rectified and they have come across with some evolved with some new technologies. So still it is under the process only. So they are not completely replicate as same as our human bones. So then come back, next example will be they will be seeing your trees, some wood. So that will be your main usage of your in engineering terms, we can able to wood is used as a main plays a major role in creating or prepare manufacturing of your papers, and then some furnitures, whatever it may be, engineering tools or many purposes wood is served as the main purpose. Then coming about to the silk, bamboo, so these are all having some functional graded approaches, so it will be used in day-to-day trying. We are now just shifting the focus to replicate as the nature exists. So we are not going to use the nature, but we are trying to replicate the existence of the nature. Okay, so these are all the some of the nature eco-friendly bio-based materials which will be applicable in the resource in our earth. So what will be the bio-based materials? So coming about to the bio-based material, before going to the entering into the bio-based material, what will be eco-friendly materials? So which will be can be used and disposed, and which will be produced, and which will minimally will have impact on your environmental conditions. So eco-friendly, if you use that eco-friendly material, you throw it out into the environment, so that will not make a huge impact. It will take some time, some days of time to get merge with the environment, so that we cannot able to make a pollution or some huge impact on the globalization. Okay, so which will be having the how we can able to say the material will be eco-friendly. So which will be of renewable resources, low energy consumption. So which will be the eco-friendly materials. When we are using eco-friendly materials, which will be having consumption of only less energy consumption during the production, then carbon emission, then non-toxic, then recyclable or biodegradable, then safe disposal, so then reduce environmental footprint. So if we come across all these points, will make material will be the material said to be as an eco-friendly material. So here we can able to see that not every eco-friendly material is a bio-based, and not every bio-based material is a biodegradable. So this thing we have to be clear with that thing. So for example, material like aluminum is eco-friendly material, but it is not a bio-based. But if you are taking a PLA, polylactic acid, it is a bio-based and biodegradable material. So these are some examples of the eco-friendly bio-based materials. So why? What is the need for eco-friendly material? So nowadays we are in school, colleges, universities, factories, some wherever if we want in a public aspect point of view, whoever may be the thing, everyone will make talking about the sustainable development goals. There will be a 17 sustainable development goals will be there. So out of which we will be having maybe concentrated on some engineering materials, on some which will falls under some 3 to 4 SDG goals. So in order to make that achieve that SDG goals, we will switch on to the sustainable engineering material, which is eco-friendly. Okay, so this is these engineering materials are critical to decarbonize the industries and reduce reliance on the finite source and minimize the wastage. So this will try to
Sorry to interrupt. I can't able to see. Sir, your slides were not changing, sir.
yes,
You can reshare your screen, sir. I think it will be correct.
yeah. Just a moment, sir. I'm reaching.
Yeah, now it is visible, sir.
Okay, fine. Can you able to see my screen?
Sir,
Can
sir,
you
no,
able to
sir.
see my screen?
Sir, it is mirroring, sir. You can show my screen anyway, like that you can. No.
Whether my screen is visible, sir?
Sir, please open the PPT, sir. And now it is okay, sir.
Yeah, now it is okay.
Fine. So this is the agenda I have set so far. Then why we have what the inference you can able to get. Then impact on the environment and some nature available material, eco-friendly materials, some bone, wood, then pure nacre, silk, bamboo. Some with some limitations will be using this nature existing materials. So then coming about to the eco-friendly materials, which will be having some minimum environmental impact with renewable resource, low energy consumption, low carbon emission, non-toxic, recycle, safe disposable, reduced environmental footprint. So likewise, we will see polylactic acid is a bio-based and biodegradable as an example, and need for the sustainable engineering materials suitable to the SDG goals with emission reduction, waste and pollution minimization, resource conservation, enhanced life cycle performance. So why the need for sustainable engineering materials is, so traditionally research is what we will do. We will use to make some composites with some natural fibers by using some metal matrix composites or some matrix will be using, and will be testing for the strength, durability, cost, manufacturability, and we'll be characterize those materials, and we'll be measure the performance, right? So but instead of the process has to be the same, but we have to focus morely on, and we have to shift our focus, or we have to add on the focus that we will be having a shifting towards a sustainability, environmental impact, carbon footprint, energy efficiency, then circular economy. So these, instead of before going to the material research or aspects or mechanical behavior or characterization of materials, so we have to consider that material whether it will be sustainable or not, or it will, whether we usage of that material. So for example, if you are introducing some new materials, if you are using that material for that particular application, then completing the lifespan of that material, you are throwing out to the environment. So it will not make a huge impact on the environment. So whether it will be like that or not, whether the manufacturer produced material by yourself, so that you have to be taken care of. So less carbon footprint, like efficiency, energy efficient. So then it will not make a much impact on climatic change. So this consideration of modern engineering will make a huge impact on the climatic change, resource scarcity, regulations, demands, and sustainable development goals. So everything, why I am talking about sustainable development goals, SDG goals means, so as the recommended by the World Health Organization, mainly we used to concentrate on recycling and the material or the product which we are sent back to the environment, it will not to make a huge impact on it. So that the mainly the biomaterials and eco-friendly materials are evolving more nowadays. Coming back to the bio-based materials, why it is important in engineering. So as we have seen, to reduce the CO2 emission, pollution, energy consumption, depletion of petroleum resources. So approximately we'll be using the 90% of the conventional plastics are derived from the petroleums. So resulting in a large amount of non-biodegradable waste can persist for centuries. So if we the materials which will be derived from the conventional plastics, if we throw to the environment, it will be more make a huge impact on the environment for about a century of time. So the bio-based materials provides pathway in a circular economy by producing a reduced dependence of fossil resources and lowering the greenhouse gas emissions. So we are manufacturing these bio-based materials which will not make a huge impact or emit more amount of toxics to the environment while during the manufacturing or preparing of your bio-based materials. So what are the bio-based materials? You will be having able to see some of the images which I have shown the bottom of the slide. First image is your flax, then hemp, then jute fiber. So likewise, so as a faculty you can also aware of all those bio-based materials, and many of them made the composites and prepared bio-based materials based on by using this bamboo, flax, hemp, sisal, jute, cellulose, starch, which will be extracted from some certain plants, and lignin, cheostan, then polylactic acid. So these are all some of the bio-based materials which are existing and evolving. So some of the jute fiber, likewise, it will be coming into the engineering usage, but in still some starch kind of extraction of starch from different varieties of plants, rare species. So likewise, it's still evolving and it is in under research. It will be not fully coming into the picture for the usage of in day-to-day life. So getting a terminology right. So what will be the combination? So we'll be concentrating the material should be bio-based and biodegradable. So which means when you are manufacturing the material, which will also make a less impact on the environment, and if you are exposing again, send back that same material to the environment, that should also will make some less impact on the environment. So that will be your bio-based and biodegradable materials. So that will be of PLA, natural fibers. So likewise, those kind of material will be falls under the bio-based and biodegradable. Then coming back to the bio-based and non-biodegradable. So if you manufacture the product, it will be having a less impact, then again send back to the environment will make some huge impact. So which will be of polyethylene, PET bottles. So likewise will make some time to make a biodegradable. So likewise those kind of materials will come under the bio-based and not biodegradable. Then petroleum, some PBAT and some PL. Then petroleum based you conventionally will be having some epoxy resins, polypropylene, polyethylene. So this a huge impact on the environment. and then again disposal of the material again back to the environment will make a huge impact. So mainly will be based on these four categories will be categorized into the bio-based and biodegradable and bio-based non-biodegradable, then petroleum-based biodegradable and petroleum-based non-biodegradable. So this we have to be maintain this clear. So from this presentation we can able to ensure that the product which you are coming across or inventing or producing or manufacturing, so such kind of thing. So when you are manufacturing that new material will be making a less impact. Then again disposal of your material after the completing of your lifespan of the particular material sent back to the environment will also make a less impact on the environment. So some materials, so some natural fiber reinforced composite materials are jute, hemp, flax, sisal, bamboo, coir, canaf. Canaf fiber also are mainly used in your bulletproof vest. So coir are used in mainly packaging industry. Some nowadays many composite sheets are evolving with that thing. Likewise low density, likewise some matrix like epoxy, polyester, bio-based resins are also there, polylactic acid. So then some will be having, these are all having the some key weakness is hydrophilic fibers absorb more moisture, batch to batch property variability. So every bio-based material will have some weakness. So we cannot able to achieve the all the mechanical properties in a better way. So somewhere we can able to get the strength, somewhere we can able to get the adapt to some particular weakness of having adaptable to the temperatures. So likewise we'll be having some weakness. So for that thing we have to concentrate more on the natural fiber to sustain or adaptable to the different environment. So that perspective point of view we should supposed to carry forward it. So some with the growing publications from the year of 2021 to 24 or until now 26 concentrated mostly on bamboo, flax and hemp fiber systems. So I have listed out the natural fiber composites, the densities, tensile strength, key trade and typical usage. Some jute will be used for packaging and panels, hemp will be used in automotive interiors, flax will be used in sports boots and panels, sisal will be used in ropes, and bamboo will be used in constructions, coir will be used in automotive textile, geotextiles, canaf will be used in panels and packaging. So these are all some of the natural fiber materials which will be used in some typical usage. That will also have some different key properties. So jute can be low cost and widely available, and hemp will be of high stiffness to weight strength ratio. So based on the if you want a better impact resistance, your flax will be sisal will be used. If you want elongation, higher elongation, coir will be used. Damping properties are also the coir will be used. Then high amount of yield strength, if you want to make use of this canaf will be used. So such a similar each natural fiber possesses a different engineering properties to enhance to adaptable to newer situations. So biopolymers. So coming natural after completing of the natural fibers, we coming to the biopolymers. So which will be your PLA, which will be derived from the cornstarch or sugarcane starch by using in which will be used in packaging, 3D printing filaments. So nowadays 3D printing are evolving and additive under the additive manufacturing techniques, which will be used 3D printing as a major thing. Many researchers are going on this making of filaments, creating of 3D print prototypes, and the complex structure also. If you want any complex structure also, you can able to make use of it. So this will help, the additive manufacturing technology will help to boom the bio-based eco-friendly materials. Why? Because we can able to make that bio-based eco-friendly material as a filament. So we use that filament to make some complex structures or complex geometries by using additive manufacturing techniques like 3D printing. Nowadays we'll be having some 4D printings also will be there. So likewise we can able to adapt and we can create n number of variable material properties and enhance your mechanical properties for different engineering applications. Okay, so next coming back to the PHA polyhydroxy alkylonics, it will be synthesized and fully biodegradable used in a medical that will be one of the biopolymer. They start with blend and cellulose. So they are infusing the cellulose and blend the starch. It will be used in for the food packaging. So normally we will be having aluminum foils for so many food packaging industries are using aluminum foil as a main thing. Nowadays, many researchers are going on a starch-based blend and cellulose-infused starch-based blend by using commonly used for the food packaging and disposable wares. So when we are going into exposing some radars or some kind of cloths, so they are using it as a disposable wares also. So that starch will be making a huge impact on the engineering material applications. Okay. Then cheostan, which will be derived from the crustacean shell, which will be biocompatible and used in a wound dressing and scaffolds. So normally we'll be having some scaffolds in a human being. So that will be making by using it as a replicating that by using it as cheostan. Then processing, it will be concentrating on foam, cup trays, or completely under which will be not explode. Okay. So some glycerin remains a dominant plasticizer across the field. So these are all some of the biopolymers. Then wood-based and mycelium composites are there. So these are all composites what will be used by using blue laminated engineering for low carbon buildings. So they are using cross-laminated timbers. Then mycelium composites want to especially build their bone with without affecting the fungal. So these are some of the wood-based composites. Then bioceramics. So coming to the bioceramics, you will be having and biodegradable metals like hydroxyapatite, then tricalcium phosphate, aluminum oxide, zirconium oxide, then silicon nitride. So these are all the most widely used bioceramics, biodegradable metals like magnesium alloys. So magnesium alloys are used in your implant screws. So if you are having some bone fracture, so there you can able to connect your bones with the help of some screws like inside the body. Some components will be placed, joints, and make it screwed on the cracked bones. So then after this will be some of material will be having some biodegradable property. So after some period of time, it will get degraded and solidify into the blood and come out of our body. So some of the materials will be existing in this thing. So kept for a period of time, and after some time makes another operation to after the joining of the bones, we will be taking one more minor operation to get out the screws. So those screws are made using this magnesium alloy, then titanium. So likewise kind of materials they will be using for the biodegradable metals. Okay, so pure magnesium will have some corrode. Pure, if you are using pure magnesium, it will be corrode in a 2 to 4 mm per year. So for example, if you are having a 2 mm thickness of plate, which will be processed inside the body operation, so it will be taken a year to corrode. So if you are using alloy or surface engineering, it will be slower to 0.3 to 1.2 mm year. So it will not corrode in a stretch. So it will take some more time. Okay. So if you are using pure magnesium, it will corrode fastly. If you are using some alloy, it based on your nature of your crack, the material will be chosen. Okay. So these class of bridges directly into the biomechanics module will return to magnesium alloy. Okay. So then protein and silk based biomaterials. So these are having a better strength to weight ratio, which is used in tissue scaffolds. So it will be having in human implants, the scaffolds will be majorly used. Then this will be based mainly on your silk fibrillum. Okay, so then keratin recovered from wool or feather waste, which will be used in wound care and regenerative films. These materials sit at direct interface, which will be of covering the materials and the biomechanics. Okay. So these are all some of the natural fiber composites, biopolymer. These are some. So far, I have explained about this natural fiber composites, biopolymer, wood-based, bioceramics, protein, silk-based. So it will be biodegradable or not. It will be what will be your engineering role over here. So first, natural fiber will be used in structural, semi-structural, lightweight engineering applications they are using. Then biopolymers will be used in packaging, food packaging, films, filaments, likewise. Wood will be used in structural building element and insulation systems. Then bioceramics and magnesium alloys will be in orthopedic and dental implants. Protein and silk based will be your wound care, tissue scaffold systems. So these are all the things which will be biodegradable is only two, biopolymer and protein silk based class will only be the fully biodegradable. Natural fiber and wood will be a partially wood will be fully biodegradable, mycelium will be partially. Then natural fiber will also which will be infused of the metal matrix composites like epoxy, polylactic acid, like those kind of things. If you are using, means it will take some more time when compared to the natural pure natural fiber composites. So these are all the overview what we have seen about the materials. So in order to characterize those materials, what will be the testing we can able to use? So especially initially we will start with the tensile flexural impact under the some ASTM standards, DIN standard, VDI standards. So many standards are there. So adopting some standards will be used to test the sample under the universal tensile machine. Then flexural impact isochart test. So likewise the mechanical characterization will be done. Then dynamic mechanical analysis to measure the viscoelastic behavior across your different temperature, how your material will be behave in a different temperature environment. Then scanning electron microscope to view the microstructure and distribution of the elements. Then XRD and X-ray diffraction. So that will be used to find out the percentage of materials present inside the if you are producing a composite, a bio-based composite material, your XRD will be replicating your percentage of material presence in the material. So this much of percentage of material 1, this much of percentage will be of material 2. So likewise we'll be having a exciting test. So then moisture absorption testing will be done to ensure the natural fiber hydrophobicity. So in order to measure those kind of things, your moisture absorption test will be done, then corrosion test will be done, then digital image correlation. So that will be one of your technique. Whether many of those will not aware of those digital image correlation, this will be a kind of viewing the stress or strain in directly with our naked eye. So this we can able to see. So that I will give you the application in my research in the application in upcoming slides and my research papers. So I will explain on that part about the digital image correlation. So it will be making a mapping of your strain without contact sensors. Okay. So then the standardization of research gap, especially newer class like mycelium composites. So these are all not aware of the test and the newly evolving composites are nowadays mycelium composites. So these to characterize those materials, these are all the main test we are going to carry out to characterize the bio-based and eco-friendly materials or the natural or some composites material, whatever you are going to manufacture the things. So hierarchy nature of your nature fiber. So what will be the thing? So initially the material, how we can able to start with that. So first of all, we'll go with the moleculars, then we'll be go with microfibrils, then fiber bundle, then composite. So how we can able to go with this kind of sequence? So initially you will be having a cellulose chain. So initially we will be having aware of atoms, bonding of electron atoms. So likewise we can able to see in physics, study in the physics about phase center cubic, body center cubic, unit cell. So likewise, so it will be have a single molecules, then it will be transformed or combined together to form microfibril. So that will be of crystalline and amorphous region. Then it turns to a bundle of microfibril to a fiber. Then making of n number of fibers will make a fiber bundle. Then it will be turns with the resin or matrix composites, which will be turns into a composites. So this will be a hierarchy of your natural fibers. So fiber matrix interface and surface treatments. So this is your some of your saline treatment, acetylation, enzymic treatment will be carried out for the fiber matrix interface and the surface treatment. So if you are having your natural fiber or matrix addition will be poor, which will be lead to a composite failure. So if your matrix will not adhere to the fiber, or your fiber strength will be of less, okay, whichever will be a poor thing will lead to a failure of your composite. So we need to focus on more mechanical properties to enhance or to so those behavior in all aspect point of view, whatever they require. Okay, we cannot able to attain all at a high point. So some wherever based on your application, high strength or high yield point we require, or high durable material, high reliable material, high toughness material. So so likewise, whichever the property we require are based on the engineering application requirement. So we need to focus on that thing, and we need to fabricate or to manufacture or to produce the metal fiber matrix interface and surface treatment techniques. Then alkalization, which will remove the surface impurities, increase the fiber roughness for mechanical interlocking. So for that thing, alkalization is done. So these are all some of the fiber matrix interface and surface treatment process which will be done on your manufacturing of your bio-based and eco-friendly materials. So then processing techniques after making your composite ready, fiber ready. So what will be making to take a final product of your as a bio-based material, which will be manufactured by using compression molding, or injection molding or additive manufacturing, then electrospinning, freeze casting. So likewise, many process are there which will be adaptable to certain process techniques. We used to select that thing and we have to go for the certain process. So for example, compression molding means it will be suitable for the thermoset biocomposites. So then if you are taking an injection molding, it will be of thermoplastics biocomposites. So likewise, based on the materials thing, we can able to go with the process, select the process. Okay, so bio-based filament and cellulose kind of filament, if you are manufacturing, can go with the additive manufacturing. Okay, so likewise, nanofiber, if you want to produce a nanofiber, so electrospinning would be used. So if you want to create a controlled architecture for tissue scaffold, freeze casting would be used. So likewise, based on your application, based on requirement, so suitable techniques will be selected for making of your bio-based materials. Then coming back, we have seen so far about the materials and the parameters and the processing techniques, then how we can able to manufacture the biomaterials. So then after the completion of the biomaterial, how we can able to validate this with the computational design approaches. So we can test your natural fiber or whatever it may be. So if you are making an eco-friendly material, if you are manufactured, you have to make some suitable for some engineering applications. So first on below I have given some different examples. Left side will be your human bodies. Somewhere I have given bottom, I have given different leg posture. Then above that I will be given some knee bones, then finger joints, then neck bones. So likewise I will be given some examples. Then second image I will be shown gear, polymer PLA gears. Then third image will be your teeth, dental implants. So these are all the different applications where the PLA or some magnesium titanium alloys or bio-based materials will be used for the engineering applications. So these, in order to use this computational design, can able to measure the readiness of your material to the particular engineering application, whether it will be adaptable to your engineering application or not. Okay, so this will be the computational design can able to evaluate your manufactured bio-based material will be applicable to your engineering application, will be adaptable, whether it will be adaptable to your engineering application or not. Okay, so some scaling, based on the scaling you will be having some level of analysis. So if it will be your like atomic, molecular or cellulose kind of thing, you will be having some molecular dynamics studies there. So that will have to be taken care of. Then if your material will be of a micro scale level, so that will be of your homogenization process. Through the homogenization process you can able to check out your material. Then if it is a meso scale, so they will be having some laminate theory will be used. Then macro scale, your FA level can be used. Okay, so these are all the multi-scale modeling techniques. So based on at what position your material is, what will be the test you can able to ensure whether it will be right or wrong. Okay, so it starts from molecular, micro scale, meso scale and macro scale. So then if we are going with a macro scale level, finite element analysis is your main technique in order to measure the mechanical and temperature bound properties. So to ensure the manufactured biomaterials for a particular application, whether it will be suitable or not. Okay, so this will be followed with some define the structures. First of all, we have to manufacture that material to a product. Then we have to design that product. Then we have to analyze that product and have some material properties like stiffness, Young's modulus, then Poisson ratio, then density. So likewise, property should be needed. That has to be incorporated. And for the design, we have to assume that material property for that design, and then we have to incorporate the meshing and then boundary conditions. So, for example, if you are doing it for some dental implant, so if you are manufacturing mandible bone, so if for that mandible bone we have some boundary condition. So we have to chunk. If you are taking a food, when we are opening our mouth and we are kept the food inside our mouth, and we have to crush that food with, by using our mandible joint, with using that will be connected to the teeth. Then teeth will be crushing your food. So likewise, the boundary condition has to be placed, and then we have to simulate by using a finite element software like ANSYS, Abacus, SolidWorks. So many analysis softwares are there. So you can able to use any one of the tool to test your biocomposites. So as I have said, we have to make some imaging, then meshing, then microscale finite element, then homogenization, then macro scale. So then after getting the results from the finite element analysis, we can able to build the model by using your machine learning techniques. So whatever the data which we have generated experimentally, and whatever the data which we have get as a result from the computational tool, like computational FEA tool like ANSYS, Abacus, SolidWorks, likewise. So incorporate that data and give that data input data, output data. We have to give it as a to the machine learning model, and we can have some different level of model. Machine learning models are there, basic models like linear regression model, then some advanced model like random forest model. So likewise, we can use some machine learning models to develop a model to get a or to different to obtain a different results. So for example, we cannot do with or we cannot able to manufacture for a different environment, for different conditions. Once one condition we can able to validate with all these things, then we can able to build a model. So validate that model. So then we can able to vary the environmental conditions. We can able to easily get your results in a fraction of time. So that will be not taken a day of time. So if you go for an experimentation, it will take some huge days, from for 2 months, 3 months of time to manufacture the start from the scratch to the end of the material. Then if you are going for the experiment, then if you are going for finite element analysis computational model, it will take some 3 to 4 days or 1 week. It will based on your element size or size of your model. It will take some days, weekdays of time. If you build a machine learning model, it will give some fraction of time you can able to solve the thing and able to get the results in a easier. So these are all some of the case studies which I have shown over here. This is not my research publication. Researchers have already used their ML techniques for biomedical engineering applications. They used additive manufacturing techniques to produce the bio-based engineering materials, and they have created a machine learning model. Okay, so for the scaffold and implants. So these will be using, they're using advanced digital twin for coupling their patient's geometry with continuously updated computational model. So digital twin is based on your advanced machine learning model that will make give you the real time digital the patient's detail to the update the patient detail towards the digital twin, can able to continuously update your computational model. But machine learning model is once created, that will be fixed. So here in the digital twin, If you can able to update the data, you can able to get your model will be an updated thing. So some applications. So there's some applications are dental implants, then hip prosthesis. We are making a hip implant, knee implant, dental implant. So then these are all the biomechanics. Apart from biomechanics, gears. So these are all the researches which I have carried out, which will be based on the bio-based materials. Okay, so here you can able to see the mechanical biocompatibility of the stiffness. So normally our bone, cortical bone will be having a less stiffness compared to the magnesium alloy. Then titanium with a combination of 6% of aluminum and 4% of vanadium will be having that implant will be of higher stiffness. Then stainless steel will be having of 200 gigapascal. So as we can able to see from this slide, our bone will be having of less stiffness when compared to the steel and magnesium and the what the material we have generated, which will be having higher stiffness as compared to the bone. So then implant stress healing. Then these are all some of the pure magnesium uncoated material, some biodegradable magnesium alloys combinations, corrosion rate, then source, how we can able to extract. Then magnesium screws, as I have said, for your implant joining of metals, what will be the screws will be used inside our body during our major or minor operations. That screw will be made of your mainly on magnesium material. So then optimization of bone scaffold and porous materials, then dental implants. So then machine learning models that I have already explained, morphology optimization. Then before going to the challenges, I will be show some of the researches which I have done. So this is one of the biomechanical evaluation of all-on-4 mandible implant using a varying posterior angulation. So what we have did this. So this is the image we can able to get from the data set from the patients directly. We can able to get this. This is a dental X-ray. So some patients will be having of due to some injuries or due to some accidents, they will be having a damage of your mandible jaws or mandible bones. So that during that time, some patients will be undergone the X-ray. So we extracted that X-ray data from directly from the patient, and we extract the data from the X-ray, and we have generated a mandible bone, that jaw bone, that what we have below your teeth, you will be having a jaw mandible bone. So that bone will be called as a mandible bone. We extracted a design from the X-ray by using your Mimic software. So then we have created that we incorporated into the computational model by using your Fusion 360. So this will be your different implant angle which we have tested. So how the implant will be done. So likewise, so here you can able to see. So we have manufactured the mandible bone by using of ABS and PLA material. So here we have some ABS material. We have manufactured the same bone with the PLA material also. So we have an implant that is screw. Here we have used the titanium with the 6% of aluminum and 4% of vanadium screws for the implant. We will be having 4 kind of implants: straight, 50 degree, 30 degree, and 45 degree implants we have did. And so this is the computational model we have developed. So experimentally we have tested, and computationally also we have tested the thing. And so this is the test setup. We have a test for compression, tensile, flexural, So likewise, those tests can be carried out by using this universal testing machine. So then we'll be having test data, and here you can able to see find the failure of the mandible bone where it is getting failed. So these are all the implant screws. So this will be your failure region. So from that, this is the experimental results. So this will be your computational results. So then we have get some chart. Okay, so what will be your deflection, implant, different implant angle, what will be your deflection, what will be your stress, compressive stress, where the maximum stress is occurred. So likewise we have analyzed. So we have compared both experimental and numerical validation. So we have solved by using computational model like a FEA, ANSYS, and here you can get the right side, you can able to see the experimental kind of thing. So from this you can able to see the validation. So for 3 different implant angle, what will be the maximum load occurred by using the experimentation. We are applied the same load on the computational model as well. Then we have predicted the deflection of that model and what will be the error percentage. So it will be below 3%. So below 5% is acceptable. So it will be attained below 5, which is nothing but 3.5 for 45 degree and 0.5 for 30 degree and 0.6 for 15 degree. So this will be your then initially we have manufactured the bone by using bio-based material like PLA. We incorporate the change the material. Once we validated this data with the experimental data with the computational data, then we have changed the material property from PLA to this our own cortical bone material. So what will be the mandible bone will be of in our human will be of cortical. So that cortical material property will be incorporated, replaced with the PLA material. Then we have tested this material using a computational time. Then we have get the deflection and we will be getting where the maximum stress has been occurred. So likewise, the time will be shaved. So we cannot able to test with the exact what will be the human. We cannot test with the human bones, right? So until or unless we will be having, we cannot get that mandible bone directly. So we have tested and validated with that PL bio-based material, PLA material. Then we incorporated that, replacing that bio-based material properties with the cortical, our human bone materials. Then we have analyzed this stress. So then we found that results and we validated. Then we have got those results. So then this is one example for dental implant. So this example, second example will be contact stress, and here of zirconia against alumina. It will be also your bio-based materials. Zirconia is that dioxide and alumina oxide, trioxide will be your all be used for your human implant like hip implant, hip prosthesis. So that we can able to find out the wear, and here you can able to see the different activity. So there are some 20 different activities like sitting down and getting up, lifting, the person who is having the person who is lifting 25 kg, the person of having some body weight of 75 kg who is stairs up, stairs down, normally walking. If they carry lifting the 40 kg, they carry 25 kg, they ladder up at different angles. So likewise will be segregated some 20 different conditions, and we have so this is the human hip joints. So this we have designed by using a computational FA, ANSYS, APDL. So then we have calculated the wear rate. So incorporated the getting the wear rate from the experimentation. Then we incorporate that experimentation coefficient of friction material towards the computation model to get the wear of the particular hip implant. So then we have find out this contact stress, contact pressure on different gait activities. So we, which condition which the wear will be more. So lifting 40, able to see group. Okay, we have segregated 20 activities into 4 groups based on your load carrying capacities. Okay, so based on this, we can able to see in the group A, you can able to see lifting 25 kg is having a higher wear. Then group B, you can able to see lifting 40 kg. The person who is having a weight of 70 kg, that 70 kg person who is lifting a 40 kg weight will be having a higher wear. So in group C also you can able to see lifting 50 kg will be having a accumulating a higher wear on the hip implant. So then here you can able to see more or less group D 40 and 50 kgs will be the same amount of wear which will be carried. So likewise, the wear prediction by using your bio-based material of zirconium oxide and aluminum oxide for your hip implant. So in the same way, silicon nitride, as by using silicon nitride as a biomaterial, bio-based material for hip implant with a biolubricant. Okay, so with the biolubricant we have used our glucose as a biolubricant. So same we can able to test out the wear for the different activities, and we have make a computational model so that we can make a SEM analysis also. So how the bonding of that silicon nitride hip implants will be there. So likewise, we have tested the contact pressure for the different activities. Same way, we have predicted the wear for all different categories. So these are all examples of some bio-based hip implant, dental implants. So coming back to the same material to the engineering side, we will be having some gear failure prediction by using your finite element computational model like finite element analysis and photoelasticity technique. So here the polymer gear will be tends to different failures like wear, thermal deformation, tooth breakage and pitting. So likewise we'll be having some different materials, PLA, some different 10 different polymers, metals, everything we have segregated it out, and the properties is been listed over here, and we have made a computational model. So then we have fabricated the PLA gear and polycarbonate gear, which will be having a birefringent property. So that can birefringent property material can only be used in your photoelasticity setup. This is the setup which we have fabricated and developed and fabricated. So that we have tested. So this is our designed the test rig. So that test rig will be kept on the photoelasticity in between the photoelasticity setup, and we have gave those experimental results in terms of fringe pattern. Then we have validated these results with the experimental, theoretical and numerical. So computationally we have verified with the 7.5 principal stress difference. Then experimentally we have got 8.01, then theoretically we got 8.79. So experimental and numerical lies within the theoretical value. So we have validated this. Then we incorporated this data into a machine learning model. So we have developed a random forest regressor model to find out the future importance, to find out the which parameters plays a major role in finding in making a gear for a failure for a gear application. So the torque and the contact width are the main influencing parameter to make the gear for a failure. So likewise a linear regression model also used. So then we have developed a machine learning model. Then we have validated that machine learning model with the already existing experimental thing. With some other researchers has did some experimentation. We have validated our results, developed a model. We have incorporated the other researcher work into that model, and we have predicted that wear. Then we have get the as same as the experimental results which we have get. So from this thing, we can able to see some of the applications we have so far the applications which will be used in your bio-based and biomechanics and in the engineering gear applications also. So what will be the challenges, future directions and takeaways are some technical challenges will be there. So we cannot able to extract some natural fibers, right? So from the growing region, we have to make some process to extract the natural fiber. Then moisture sensitivity, then higher temperature exposure. Then lab scale we cannot able to scale up or scale down. So then likewise kind of difficulties will be facing in a technical way. Then computationally we'll be having a system challenge. So for example, we required a higher performance system with a higher end of specification systems to make a computational work. So likewise, we will be having some versatile experimental data sets, or we need require more huge data sets for computational challenge. Okay, so we need a property, different kind of property has to be incorporated into the computational, so that finding of that particular properties of the material, then scaling of the material, creating a geometry of the material. So we can able to create a complex geometry also in a computational way, but it makes some huge challenge behind that. Okay, we cannot able to, or we cannot nowadays we can able to get a 3D scanning and all. So reverse engineering we can able to do that. So through we can able to connect some engineering technologies to tackle the challenges whichever we are facing. Okay. So then in your life cycle, regular and life cycle challenges are you cannot able to get a certification, then you cannot able to reduce automatically, you cannot reduce the lower carbon footprint, life cycle assessments, so standardization. So these are all some of the life cycle challenges are there. So then where the field is heading, so how we can able to make ourselves ready, right? So these are all some of the emerging researches has to be focused on bio-based composites, bio-based materials and eco-friendly sustainable materials. So which is of nanocellulose reinforced composites, which is not somewhere it is going around, but we are not concentrating more on we are concentrating on making of composites. Instead of that, we cannot able to infuse the into a cellulose level or nanocellulose level. So nano infused composites kind of thing we cannot expose the so far. That is one of your emerging. Then self-healing biocomposites, then smart biodegradable material with sensing capability. The material which should be having some sensing capability, so that we have to be in the emerging field. Then 4D bioprinting materials, then AI-driven inverse material design, digital twin, sustainable manufacturing using additive manufacturing and green processing technologies. So these are all some of the key emerging field in the bio-based composite materials, eco-friendly and sustainable materials. So the key takeaway session from this session is a bio-based material can meet a real engineering performance, which will be of sustainability and performance are not automatically in attention. So then computational design FEA is what makes rigorous design possible despite of natural material variability. Then biomechanics is ideal, providing ground biological tissue itself performance target through mechanical biocompatibility. Then dental implant, orthopedic device, tissue scaffolds are all now active set of computational design researches are not just for future promise. So these field harvest one problem are much more data validation regulation is about material themselves. So these are all some of the references. And the future of engineering materials may not be about inventing something entirely new. We cannot able to say that entirely we have to discover a new thing, but we can rediscover, refine and scale up with some already existing thing is also making a huge impact on the environment. So thank you one and all for giving me this opportunity. Now I will be open the session for the questions and discussions.
Sir, thank you for your wonderful presentation, sir. Now participants can post their queries in the chat box so that professor will reply.
Best 3D printing technology for bioimplant. So, best 3D technology is manufacturing of the bio-based filaments, actually. So, if we have to concentrate, still the researches are going on. Actually, I'm also working on the creation of natural bio-infused filaments. So, that parameters making a huge response and is a needy thing for making of bio-based filaments. So that to be adapted to the 3D printing technologies.
Thank you, sir.
Thank you, sir.
Participants, you can post your question in the chat box. Sir, another question, sir. Sir, which bioimplant material can be a composite?
So, as we have shown, the titanium, aluminum, vanadium composites are now emerging in the medical field. They are using for mainly hip implants, knee implants. Likewise, they are using some titanium, which will be of a not a biodegradable material, actually of bio-based materials. So that will be of a composite only. It will be composing of titanium, aluminum and vanadium. So that will be using nowadays, evolving more. But the natural infused biocomposites are still in research. They are not incorporated into the field, enter into the field so far. So right now we'll be having bio-based material only, not biodegradable material, as composite, as we have said, composite materials.
Okay, sir. Sir, with this we shall wind up for this session, sir. Another question, sir. Any special storage space
required for storing biodegradable composite before using? Actually, the special storage thing to be maintained for bio implants, it is needed actually. So why? Because it should not contaminate with the environment, or it should not get. For example, if you are making of human implants, all implants should be stored in separate containers or enclosed vacuum enclosed containers, so that it will be fixed inside the body, right? It should not get any kind of infection or any contamination, or any environmental impact should not be made inside our body. So storage should be capable. Storage is required for storing these biodegradable composites before using directly into the for example, if you are making of human implants, so that is must needed thing. So if we are keeping that inside the storage also, it should not have to make should not change any properties inside that thing. So any other questions?
So I think there is no question, sir. We shall wind up the session, sir. Thank you for your wonderful presentation, sir. Hope the participants would have benefited from
Okay.
your presentation, sir.
Thank you for giving me this wonderful opportunity. Thank you.
Thank you so much, sir.
Thank you. Thank you, sir.
Yes, sir.
Shall I leave, sir?
Yes, sir, you can, sir.
Yeah, thank you.
Yes, sir. I request participants to join for the afternoon session around 12:45 p.m. Dr. Vardhini Madam from Urban College of Engineering, Srirangam, will deliver a lecture on 3D printing with the FDM technology. So please be on time. Thank you. Connection is lost.